Okay, in this video we're going to go over chapter 4 in our textbook, and it's entitled More on Differentiation. So the first thing I want to tell you is that this section 4.1 is a very important section in calculus because it's all about using calculus to optimize, so that's either to maximize the situation or to minimize the situation. So what I've done here is I've written down our steps. So the first thing you're going to do is you take your function and you take the first derivative of the function. You then set the derivative equal to 0, and the x's you find will be the critical values. So those will be the x values that potentially have a max or a min. It could also have a shelf, but we'll talk about that later. Third step, these critical values are the independent variables, as I said, that yield possibly a max or a min. Fourth step, you're going to test the critical values using the first derivative test. Okay, there's a second derivative test also, but we're not going to do that right now. And then you're going to express the results of your test on a sign chart. And in step 5, whenever you make a sign chart, you have to have a statement that goes along with it. And then you're going to solve for the max or min value of the function using the critical value. So the max or min value of the function is the y value. So you get to evaluate your original function using the critical values that you've identified. Okay, we're going to go through this example on the next page. Okay, so here's our first example. So you've been asked to determine the smallest value attained by the function using calculus. So you're basically going to find the minimum value of the function. So here's your function, your f of x, and what you're going to do is you're going to take the first derivative, and doing that and using the power rule, you get 2x minus 8. Set that equal to 0, solve for your x, and you get 4. That is your critical value. Okay, here is your sign chart. You put your critical value on the sign chart. Then you're going to pick a number to the left of 4. So let's say we're going to pick 3. Take this 3 and evaluate your first derivative. So plugging in a 3, I get 3 times 2 is 6 minus 8. So I'm going to have a negative value. So that's why I have a negative on the sign chart above where the 3 would be. Then pick a number to the right of 4. What I'm doing is I'm seeing how the slope is changing. Okay, so the right of 4, I pick a number like 5. I'm going to get a positive value. So I'm going to erase that 3 for a second. And I'm going to do a little sketch of what my function is looking like. So what's happening, so let me just see one thing. Yeah, what's happening is I'm going to erase this as well. So at the critical value, your slope is 0. Okay, that's why we set it equal to 0. To the left of the critical value, your slope is negative. Negative, 0, positive. At 4, you have a minimum. Okay, so here's your statement. To the left of the critical value, the slope is negative, and therefore it looks like this. To the right of the critical value, the slope is positive. The function, therefore, has a minimum at the critical value of 4. Okay, so now, what is the function value? You're going to plug in the 4, and here is your function value. At the minimum, the function value will be negative 6. So that's our first example. Okay, let's go through the next example on the next page. Okay, so in the second example, we've been asked to determine the largest value attained by the function using calculus. So here's your function, your f of x. Take your first derivative, set it equal to 0. You're finding where the slope of the first derivative is 0. That's your critical value. It is negative 6. Put the critical value on your sign chart. Pick a number to the left of negative 6. Plug it in your slope. You're going to get a positive. Pick a number to the right of negative 6. Plug it in the slope. You're going to get a negative. This is what your function looks like. Your slope is positive to the left, 0 right at -6. Your slope is negative to the right. You have a max. So here's your statement. To the left of the critical value, the slope is positive. To the right of the critical value, the slope is negative. And therefore, the function has a max at the critical value of -6. What is that critical, what's the result of the critical value being put in your f of x function? That gives you the max at 38. So far we've talked about the critical value. The critical point is the x and y. So your critical point would be -6, 38. What is that critical point? That is just your vertex in this situation. Okay, just your vertex. It is the critical point if it has the x and the y. Okay, let's go on to the next page. Okay, here's kind of a neat problem from page 164, number 7. So they have a sheet of paper or construction paper, cardboard paper, whatever, and they want to maximize the volume of a box made of this 10 by 10 paper. So what they're going to do to make a box, they're going to cut out the corners and fold it up. So you want to figure out if you have a piece of paper or a piece of cardboard that's 10 by 10, what are the dimensions that you're going to cut out of the corners so that when you fold it up, you have a box of the maximum volume. Okay, so this is what we're going to talk about. Here is your picture over here. You're going to cut here, 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 here. They're all going to be little squares. So what are your measurements of your box to be? So let's see. That was 10. Now it's 10 minus 2x because I'm going to say that I'm cutting out a box that's x by x. I'm just not sure what the x is going to be. So if that is your width, what's your length? Your length is also going to be 10 minus 2x. And then what's the height when you fold it up? It's going to be x. So here is my volume expression. So when I go ahead and multiply it all out, I get a cubic, which makes perfect sense because we're talking about volume. So volume is a cubic measurement. So I want to maximize the volume, so I'm going to do an optimization. So take your first derivative and set it equal to 0. And in this situation, I ended up having to do the quadratic formula, or you can use your graphing calculator and get your roots of the first derivative, because that's what I'm looking for, where it goes to 0, so where it crosses the x-axis. So I have two roots. One's a 1.7 and one's a 5. So I need to figure out, if I want to maximize volume, which one's going to do that. So I have my two critical values. Here's my chart right here. And what I'm going to do is I'm going to test to the left and to the right of 1.7 and to the left and to the right of 5. And what I'm noticing is I have positive slope to the left of the critical value of 1.7, so it looks like this, the function. Then it comes down and it's going to have another, it's going to have another 0. This is misbehaving a little bit. It's going to have another 0 right there, so that's another slope of 0, and then it's going to come back up. So clearly the 5, as you can see from the statement, the 5 is going to be a min, and the 1.7 will be a max. So if we want to maximize the size of our box that we can make by this 10 by 10 piece of cardboard, we want to cut out an x that equals 1.7 times 1.7. So what is the volume that we're going to get when we do that? Well, if we evaluate our original function, here's our original function, and we're going to evaluate it at 1.7, we will get 74.05 cubic inches of volume. So that's a nice application of our volume problem. And it's a simple optimization, and it's something that you should be able to do. So let's go on to the bottom of this page. Okay, so now that you know about this optimization, which is a fancy thing for just saying take your derivative, set it equal to 0, and find the possible maxes and mins, you can use this technique to maximize profit. You want to know that profit is total revenue minus total cost. You can maximize revenue, and revenue is just price times quantity. You can minimize your costs. And I have a quick word about price. So if they give you the price, the way you get revenue is, say, price times quantity. Sometimes they'll give you the price as an equation. And that's the case. Your total revenue is still price times quantity, but you'll end up having a quadratic for your total revenue equation. Okay, so let's go on and we'll do some more optimization. You want to memorize these relationships. You want to know what profit is. You want to know what revenue is, that is price times quantity. You want to know about the downward sloping demand curve. So we're going to try to do a minimization of cost using calculus on the next slide. Okay, so here's the cost function right here, and you're going to find the minimum marginal cost. So take your first derivative, set it equal to 0, and you're going to solve for your critical value. So go ahead and do that, and then I'll catch up with you. Okay, so when I did this problem, I got only one critical value. So I think we have a double root. So anyway, you're going to have a critical value, and I have a critical value of 3.8. So here's my 3.8, and I'm going to check to the left and to the right, and this is what I'm getting. And so that tells me that I have a minimum right here. So I would have a statement that says that. So you always have to have a statement. I'm not going to write it all out. Maybe I will. So how about at CV equals 3.8, the slope, and that's m, changes from negative to positive. Okay, therefore, we have a min. All right, so that's your statement. So then the question is, well, what is the min? Because I just know that if I produce 3.8 widgets, I minimize my costs. So you're going to have to take your cost equation and plug in the 3.8. And I believe when I did that, I got a minimum cost of $11.27. So just check my math, make sure I'm all good. And then we're going to go on to a demand and revenue curve next. Okay, here's our next problem. So it's a demand equation for a certain commodity is this. So this is your price. Okay, our job is going to be to maximize the revenue. So what is going to happen here? So let's think about what this looks like. Right here, what I have is a price equation. So my x is on the horizontal axis, and my price is on the vertical axis. This kind of looks like this. So it comes down like this, and here's where our 60 is, and here's where our 0 is. So they would like to have us operate between 0 and 60, which makes kind of sense. So that's the quantity that we're going to be working on. So given that, they say find the value of x and the corresponding price that will maximize revenue. So we have to first say that revenue is price times quantity. So if that is the case, then our total revenue is going to be 1/12 x cubed, right, because I'm multiplying it by x, minus 10x squared plus 300x. Take your first derivative, and after you reduce, you should get 1/4 x squared minus 20x plus 300. Set that equal to 0 to get your critical value. You should end up with critical values of 20 and 60. Here comes the sign chart. 20, 60. I'm going to check on either side My slope is positive here, negative here, positive here. Make sure you can pick numbers to do that and get the same results I'm getting. Here's the shape of my curve. It must go like this and then like this. Okay, this is my function curve. So my statement is going to be, at the critical value of 20, the slope goes from positive to negative, and therefore I have a max, while at the critical value of 60, the slope goes from negative to positive, and that will give me a min. So I want to operate where x is 20. So what do I know about that? If first off, if I want to figure out the price, because that's one thing they asked me to do, find the price also, take your price and evaluate it at 20, and you're going to charge a price of 133.33 so that you can actually sell 20 of the items. If you instead wanted to operate at 60, in order to sell that much, interesting enough, you're going to find that the price is going to be set at 0, which clearly is going to minimize your profits or your total revenues. So that's how you handle this problem. And let's move on to the next one. Okay, so here's a profit example. So I've given you total revenue and I've given you total cost. So you've got to remember that profit is just total revenue minus total cost. So I'm going to clean things up a little bit. So it's going to take me 2 steps. I'm going to do it in 1 step. So if you combine these 2 equations and say total revenue minus total cost, you should ultimately be getting the fact that profit is 200x minus 50x squared minus 182. So when I combine those 2 equations, I get that. So that's my profit equation. So take your first derivative, and you're going to get, let's see, I have them in the wrong order, but that's okay, 20 minus 100x. Okay, when you solve for x, you are going to be getting 2. So that means that if you sell 2 units of whatever it is, you will maximize potentially your profit. We don't know for certain, but let's do a sign chart to see. Here's your sign chart. Here's the 2. Check your slope on either side. If you have a number less than 2, you're going to find that the slope is positive. And if it's bigger than 2, you're going to find that it's negative. Here is what your function looks like in terms of its slope. And so you can say that at CV equals 2, the slope changes from positive to negative, and therefore we have a max. Okay, so that's nice. So tell me, what is that profit that we're maximizing? So evaluate profit at 2, and you should get a profit of $18. I also got to ask you, well, what's the total revenue then? So total revenue of 2 is going to be $312. Total cost of 2 will be $294. So you can answer a lot of questions on this one problem. Okay, we're going to go through 4.2, which is curve sketching, in the next slide. Okay, I've summarized some curve sketching items here. So the first derivative was an indication of slope. Okay, taking the second derivative gives us an indication of concavity. So if the second derivative is greater than 0, so if it's positive, your function is concave up. If the second derivative is negative, your function is concave down. And these little faces are very helpful. When your second derivative is 0, you have found the inflection point. And the inflection point is where the concavity is changing from either concave up to concave down, or from concave down to concave up. Okay, so this is important to understand in terms of how you analyze the second derivative. So an example of curve sketching we can do with this problem. So curve sketching, ideally, you're not going to use your calculator. So in this problem, we're going to have a couple of good insights that we haven't yet come up against. So take your first derivative. So my first derivative ends up being 3x squared minus 12x plus 12. Okay, go ahead and take your second derivative because we haven't really done this. So that's going to be 6x minus 12. So a little thing to note. If your original function is a cubic, your first derivative is a quadratic, and your second derivative is going to be a line. So you're always going to see this pattern. So we know to get the critical values, and that's where the potential max or mins are, you set your first derivative equal to 0. So when you do that, you end up having a factorable problem, and the factors end up being x minus 2 and another x minus 2. Okay? So my critical value ends up being 2. So I'm going to now do a sign chart. I put my 2, I check to the left, so I plug like 1 into f prime of x, and I get a positive. I check to the right, and I plug in, say, 3 into f prime of x, and I get another positive. Now I have no sign change. So what does that mean? That means that I don't have a max or a min. Instead, I have a shelf. So a shelf means that my concavity is changing, but I neither have a max nor a min. So what does that look like? So if you were to look at this function, and in terms of curve sketching, oh, another little fun fact before I get into curve sketching. Set your second derivative equal to 0, and what do you find? You find the inflection point is also at 2. So x equals 2 when you set it equal to 0. So that verifies that I have a shelf because my shelf is indeed an inflection point. So let me erase a little bit of this over here so I can give you an idea of what this sketch is going to look like. So our original function actually looks like this. Here's our 2, and when our function, and here's our negative 6, because I see that the function has a y value of negative 6 when x is 0. So my function is going to come up, and it's going to get to 2, and it's going to level off and then continue up. So here is my shelf. So you see how the slope is positive here and still positive here? So in terms of curve sketching, I would be able to sketch a shelf based on the first and second derivative test. Okay? So that's a little fun fact about curve sketching. We have one more curve sketching example. We'll do that on the next page. Okay, here's our second curve sketching exercise. So we know it's all about derivatives, so take your first derivative, and you should be getting 3x squared minus 4x minus 15. We're going to set that equal to 0, and that is factorable, so I end up getting 3x plus 5 times x minus 3. So I have two critical values. One is negative 5/3 and one is positive 3. So let's go ahead and we will set up our sign chart, negative 5/3 and 3. We do the sign chart, we get a positive, a negative, a positive. So my curve, my original function looks like this. It comes up, comes down, and comes up again. So I can see that I have a max at negative 5/3 and a min at 3, and I would write a statement to that effect. Now go ahead and you can do your second derivative. So my second derivative, I'm expecting a line, and it's going to be 6x minus 4. So set that equal to 0, and I'm getting x equals, what, 2/3. 2/3 is the x value of my inflection point. And look, it's right in here. So if my function is concave down, around -5/3 and concave up around 3, then clearly it must change somewhere, and this is where it changes. So I can now go ahead and I could graph this function. So what do I know? I know that if it's plus 2, at the end it's going to go through 2, and without doing a whole lot of work, what I'm going to figure out is at 3, I'm going to have a min, and at -5/3, so that's almost at -2, right? I'm going to have a max. So I'm going to go say max, change inflection to a min. Okay, now I have not verified where my y's are, but in terms of curve sketching, I can get a sense of the shape of the curve. I'm not getting a sense of how high my y values or how low my y values are, but I can get an indication of the curve itself just by analyzing my first and second derivatives and knowing what the inflection point does. Okay, so I'm going to leave you with that. We're going to go on to 4.3, which talks about taking derivatives when you have an exponential function. Okay, so this is another derivative rule for us, and here it is right here. If you're going to take a derivative of e raised to some function, the way you do it is you write down exactly what you see, and then you multiply that by the derivative of the exponent. So here is another example, and we're going to do questions 1 to 13 just to kind of get the hang of it. Okay, so in this section, it's all about taking derivatives of e's. So here's my first one. F prime of x is going to be 4/5 e to the x. The constant, the coefficient comes along. The derivative of x is just 1, so I'm going to leave it like that. And then minus 15x to the 4th and plus 6. So there's question 1 done. Okay, let's go on to the next questions on the next page. Okay, so here's question 3. So I'm going to take the derivative. F prime of x is going to be, write down what you see initially. Okay, and then multiply that times the derivative of the exponent. So that's going to be 2x minus 1. Okay, that's your derivative. Okay, let's look at 5. Okay, the first thing I would do is rewrite it so that it conforms to the power rule. So g of x equals e to the 2x minus 1 raised to the 1/2 power. Okay, g prime of x. First you're going to do the power rule. So 1/2, don't touch this, e to the 2x minus 1 to the -1/2. Now take the derivative of what's inside. So you write down exactly what you see, and then you take the derivative of the exponent, which is just going to be 2. Okay, so let's take another second to clean this up a little bit. The 2 in the back cancels the 2 in the front, so I'm just going to end up having e to the 2x minus 1 in the numerator, and then radical e to the 2x minus 1 in the denominator. Now, what's going to happen is, doesn't that just equal, so hold on, doesn't that just equal radical e to the 2x minus 1 in the numerator? Because if this was, well, think of a number that you can, think of numbers that you can work with, but this is the square root, this is the first power, so don't you write the power, write the base once and then subtract the exponents, and 1 minus 1/2 is 1/2, and so your final answer will be just that. Okay, I think we have room to be able to do 7 right here. So f prime of x, I see function times function, so I've got to do the product rule. Left d right plus right d left. Done. Okay, 9 is a little bit more exciting. I'm going to first rewrite it. So let's see how we're going to do this. If I have enough space, I think I do. So I'm rewriting it first, and I'm rewriting it as x e to the 2x raised to the 1/3 power. So g prime of x will equal 1/3. Don't touch anything. Leave it just the way it is. Okay, and then that's raised to the negative 2/3 power. Now we have to do the product rule. So I'm going to put a little box, left, d right, which is going to be 2 e2x, see if you can figure out why, plus right, d left. And then you certainly could clean that up. I don't have enough space right now to do that, but you get a sense of what we're getting. Okay, we have 2 more problems to do, and then we're done. Okay, so we've left the 2 quotient rules for last. So f prime of x equals low. So write down exactly what you see, and you probably want to put it in parens. D high. So d high, write what you see, e to the negative 5x plus 1, and then multiply that by the derivative of the exponent, which is negative 5. Okay, so what we're going to do is we're just going to do one at a time. So that's our first term. I did low, d high, minus high, so write what you see there. We're not taking a derivative. D low, you're going to need your parentheses, so I'm going to have 4x cubed plus 2x all over x to the 4th plus x squared plus 4, and that's going to be squared. Okay, so you probably want to, clean this up a little bit. I'm going to leave that for you to do, but that's the essence of that problem. So let's do the last problem, number 13. We've done the odds, and you may want to just check in the back of the book and see see if you would get the same answer that they're getting when they clean it up. So let's do problem 13 next. Okay, another little quotient rule. So f prime of x equals low, okay, d high, which is just 1, minus high, d low. So the derivative of 1 is 0, and then we have the little product rule, don't we? So I'm going to say, let's see, left, d right, plus right, and d left is 1. Okay, that's my whole numerator, all over 1 plus x e to the x squared. And again, you can clean this up. Why don't we take one more step? Look at the numerator. I have 1 plus x e to the x minus x squared e to the x minus x e to the x all over 1 plus x e to the x squared. So what I'm seeing is that these will cancel, and I'm going to be left with 1 minus x squared ex in the numerator. All right, so you probably want to practice more of these to make sure you understand how to deal with e to the x, and then go back and practice your optimization as well.